Welcome to this explainer. I'm super excited to have you here today because we're going to unpack something you've probably seen plastered across rugged phones, tactical gear, and heavy-duty industrial hardware. Yeah, I'm talking about MIL-STD-810H. Today, we're tearing down the marketing buzzwords to look at what this standard truly is, a highly robust, incredibly detailed environmental engineering framework. We're going to see exactly how hardware gets pushed to its absolute limits way before it ever hits the field.
Okay, so let's dive right into this. The absolute cornerstone of everything we're talking about today really boils down to this: a claim of MIL-STD-810H compliant without specific method numbers. Well, that's a marketing claim, not a verifiable one. You see, just slapping the standard's name on a box doesn't actually mean much on its own. If a manufacturer isn't telling you exactly which test methods were used and at what severity, they just aren't giving you the verifiable engineering reality of what that device can actually survive.
So here's our roadmap for today's explainer. We're going to cover 1. What exactly is MIL-STD-810H? 2. The shift from Revision G to Revision H. 3. The tailoring process. 4. Life cycle environmental profiles. 5. Core test methods. And finally, 6. The value of compliance. Let's get to it. Section 1. What is MIL-STD-810H?
At its core, MIL-STD-810H is a U.S. Department of Defense standard. But wait, it's not a checklist. Actually, scratch that. It is definitely not just a checklist. It's a comprehensive set of test methods and engineering directions for looking at the environmental stresses materials and products face throughout their entire service life. Now here's the real secret. This standard doesn't have universal pass or fail limits. Let me repeat that, because it's absolutely crucial. There is no universal pass or fail. Instead, it acts as a guide for engineers to test a product's limits against the real-world environmental stresses it's actually going to experience. It's used heavily by the U.S. military, for sure, but it's also become the absolute gold standard for rugged commercial products across aerospace, automotive, agriculture, and even the medical field.
Moving on to Section 2, Revision G versus H. This is where things get really interesting, showing exactly how the standard evolved. Back in 2008, the MIL-STD-810G revision was heavily focused on traditional, generic lab-based tests, steady-state temperatures, and pretty limited multi-axis vibration. Fast forward to the H revision in 2019, and it's a totally different ballgame. It introduces a heavily data-driven approach that focuses on real-world mission profiles. Devices are now tested against dynamic temperature cycling that mimics rapid environmental shifts, alongside significantly enhanced multi-axis vibration testing. Basically, it's a massive shift from testing a device in some abstract, static laboratory vacuum to testing how it will actually survive a highly dynamic, messy, real-world deployment.
Section 3. The tailoring process.
Tailoring is really the core philosophy of the whole standard. It's the process of altering material, design, and test criteria to perfectly match the specific environmental conditions a piece of hardware will likely encounter. Let's de-jargonize that a bit, shall we? It simply means engineers can't just open a book and apply a blanket test to every piece of gear. In fact, it's completely invalid to just call out all the methods in this standard in a blanket fashion. Instead, engineers absolutely must customize the stress data based on the specific platform and the specific environmental forcing functions the hardware is going to face. I mean, think about it. A desktop computer sitting in a climate-controlled command center needs a vastly tailored test compared to a radio strapped to a soldier in a blowing sandstorm, right?
All right, Section 4. The life cycle environmental profile.
Now, this is how that tailoring workflow actually plays out in practice, directly mapped out in a life cycle environmental profile, or LCEF. It starts right at the top, with a platform, like an aircraft, its installation location, and its geographic region. From there, engineers break that down into specific, individual missions. And then those missions are broken down even further into specific phases. We're talking start, takeoff, climb, cruise, and landing. For every single one of those phases, they calculate the exact temperature, humidity, altitude, and vibration that the hardware will experience. This incredibly detailed mapping is what generates the actual test profile. You're never just guessing. You're deriving the exact laboratory test parameters straight from the life cycle of the mission.
Which brings us to Section 5. The core test methods.
150,000. That's a massive number, and we're talking about feet and altitude here. Under Method 505.6 for low pressure and altitude testing, the new Revision H significantly expanded the testing range. The old standard maxed out at 100,000 feet, But to keep pace with modern tech, Revision H pushes testing all the way up to 150,000 feet. That accommodates modern high-altitude unmanned aerial vehicles, UAVs, and even space applications. This method specifically determines if a material can withstand and operate normally in severely low-pressure environments.
Next up is dynamic temperature testing. Remember how we said the old standard used static, steady states? Well, under method 501.7 for high temperature and method 502.7 for low temperature, the focus shifted to dynamic cycling. Imagine a device shifting from a freezing -40 degrees Celsius up to a blistering 70 degrees Celsius. The standard change rate is tightly controlled, so it doesn't exceed 3 degrees Celsius per minute. This perfectly mimics rapid real-world environmental changes, like moving a device from a climate-controlled cargo hold straight out into a scorching desert, making sure the equipment doesn't just completely fail when the temperature violently shifts.
Now, for extreme thermal shocks, we look at method 503.7. When engineers foresee incredibly sudden temperature changes in a product's life cycle, picture an airborne deployment where a device drops from a heated aircraft cabin right into freezing high-altitude air in mere seconds. They use this method. For true thermal shock simulation, the temperature change rate has to be greater than 10 degrees Celsius, which is 18 degrees Fahrenheit, every single minute. That extreme transfer rate is explicitly designed to test the hardware's ultimate breaking points, hunting for mechanical fatigue or electrical shorts caused by rapid expansion and contraction.
Here's another striking number for you: 2,000. This refers to hertz, and it applies to method 514.8 for vibration testing. In the older G standard, frequency ranges often hovered around 500 Hz, but Revision H pushes enhanced multi-axis vibration testing all the way up to 2000 Hz. This multi-axis testing basically simulates vibrations coming from multiple directions at once, which is absolutely critical for hardware mounted inside ground vehicles and aircraft. It ensures those intense vibrations won't cause mechanical fatigue, abrasion, or degrading of the electronics. And right alongside this is method 516 for shock and transit drop, which guarantees the device can actually survive the violent physical impacts of being dropped or mishandled out in the field.
And this is where it all comes together. Method 520.5 tests combined environments, because let's be real, in the actual world, your device isn't just hot or just vibrating. It's often hot, vibrating, at a high altitude, and in a wildly humid environment, all at the exact same time. This method evaluates these synergistic stresses based on detailed analysis from the life cycle environmental profile we talked about earlier. It tests temperature, altitude, humidity, input electrical power, and vibration simultaneously. The goal? To make absolutely sure the hardware doesn't fail when the real world throws the whole shebang at it all at once. Finally, Section 6, the value of compliance.
Now, upgrading to these highly rigorous Revision H test methods might bump up a manufacturer's initial R&D and testing costs by an estimated 15 to 20%, but the benefits, they're undeniable. First off, it future-proofs compliance. By aligning with modern challenges like drone ops and IoT edge devices, the hardware is ready for tomorrow's battlefield or industrial site. Second, it achieves massively higher reliability by accurately replicating dynamic real-world environments, greatly reducing field failures. And finally, it delivers a huge competitive edge. But proving this requires strict administrative rigor. Testing has to be conducted in labs holding ISO/IEC 17025 or A2LA accreditations. When a company can produce a detailed environmental test plan, a DETP, followed by a verified environmental test report proving their design survived, well, they become the prime choice for heavy industrial and defense buyers.
I want to leave you with a provocative question based on everything we've explored today. The next time you're sourcing rugged hardware, or the next time you see a flashy marketing banner proudly proclaiming MIL-STD-810H, ask yourself this: are you just asking for a standard, or are you demanding an environmental profile? Because, as we now know, without the tailored test methods and the life cycle data to back it up, it's really just a name on a box. Demand the engineering reality. Thank you so much for joining me for this explainer, and remember to keep asking those tough questions.
Like and subscribe.